And today we have Professor Rong Luo from West Virginia University, and we'll talk about noisy flows and signed graphs.
Yes. Okay, yes. Good afternoon, and thanks for coming. Thanks, Sunny, for like special arrangement to give a talk here. I know that your regular seminar is tomorrow, Tuesdays. So today I'm going to talk about the modular flows and integer flows of signed graphs. So this talk basically is a survey. It's not like a specific talk, result. So I have been working on flows of signed graphs for like 10 years. So I have a bunch of collaborators, including sorry, there should be double T here, the massive boss, and some students and my visitors. So let me start with the flows of unsigned graphs. So you give me a graph G and give each edge orientation. So D is the orientation of G. And then for each edge I assign some weight. So usually we just use integers. And the notation here is E minus V is a set of oriented in edges. For instance, for this one, if you look at the orientation here, so we have two in edges. So E minus V with two edges here, E plus is the set of out edges. So then assign weight on each edge, usually we just use integers. So the orientation together with the weight function f is called integer flow if at each vertex the total inflow equals the total outflow. For instance, if you look at this vertex, fingers are better. So for this one, you can look at this vertex, you can see that we have two edges oriented in, so the total inflow is -3 plus 0, which is -3, and one edge oriented out, so the outflow is -3. So inflow is -3, outflow is -3. And look at this vertex, we have two edges still so this is one and this one. So the total inflow is 2, and we have two edges oriented out, so 0, 2, so the total outflow is also 2. So at this vertex, inflow equals outflow. So you can check that at each vertex, the total inflow equals total outflow. So this is integer flow. And usually, K flow means what? Means the flow value cannot be very large. So K flow means the absolute value of each edge is at most K minus 1. It's not K here, so it's K minus 1. Of course, you can assign 0 to each edge, so that's not okay. So also, and if the weight of the edge is 0, we can ignore it. So we're more interested in nowhere 0. So the K flow is nowhere 0 if the flow value of each edge is non-zero. So this one is not a nowhere 0 flow. So let's look at the example here. So this is K4, and we have you can see that at vertex V, the center vertex V, we have two edges oriented out. So the total outflow is 1 plus 1, which is 2, and we have one edge oriented in, so the inflow is 2. So the inflow is 2, outflow is 2. And look at this one, the V2, you can see that all three edges are oriented out in. So the total inflow is -3 plus 1 plus 2, which is 0. There's no edge oriented out, so this outflow is 0. So it's inflow equal to outflow. You can check the V1, V2, V1, V3, so the inflow equal to outflow. And you can see that no edge has 0 weight, so there's nowhere 0 flow. And the maximum absolute value of the weight is 3, which is 4 minus 1. So this is nowhere 0 4 flow. It's not nowhere 0 view. So he proves that for a pre-genus plane graph, it is first calculable if and only if it admits nowhere 0 K flow. So in other words, the four-color theorem is equivalent to that every pre-genus planar graph admits a nowhere 0 4 flow. More generally, if you look at the graph, it's a sphere. We know the planar graph means you can just draw the graph on sphere. So more generally, you can look at an orientable surface. So if G is bridging this graph, strongly embedded in an orientable surface. So what does the strongly embedded mean? Roughly speaking, that means each edge should be on the boundary of two different faces. So it's called strongly embedded. Now then, we can prove that G is first calculable implies G admits nowhere 0 K flow. Unlike the plane graph, it means first calculable if and only if nowhere 0 K flow. But in general, for the general orientable surface, there's only one direction. It's not if and only if. First calculable implies lower zero K flow. And there are three famous conjectures due to Tutte on the flows of unsigned graph. Three-flow conjecture, which says every four-edge kinetic graph admits no zero three flow. And right now, then the best result is every six-edge kinetic graph admits no zero three flow. Four-flow conjecture means that bridges graph without piece minor admits no zero four flow. And more generally, five-flow conjecture tells us every bridges graph admits no zero five flow. So the best result is due to CMOS that every bridges graph admits no zero six flow. So from this point, okay, if you look at this result, you can also see that in general, the first calculable implies no zero K flow is only one direction, because we know that in general, if you just look at the graph embedded on orientable surface, the first chromatic number could be arbitrarily large. But the flow value is, we know that it's most 6. And one way is we don't have to look at the integers. Suppose we don't have to require them to exact the same. We can just simply look at the total inflow is congruent to the total outflow modulo K. In other words, we don't look at the integers. We just look at the flow values to be in ZK. So modulo flow means the total inflow equal to total outflow modulo K. So from the definition, it looks like that the modulo K flow is weaker. Looks like they're weaker than the integer flow, right? Because for the integer K flow, they have to exact the same. But here we just only to modulo K. However, Tutte proves that a graph admits no zero integer K flow if and only if it admits no zero modulo K flow, or sometimes we just use ZK flow. Modulo K flow is ZK flow. So this theorem is very nice because it gives us a very nice tool to approach the integer flows of lots of conjectures. Actually, in the area of flows, lots of almost all the landmarks results, such as the four flow and 8 flow theorem by Bouchet, the 6 flow theorem by Seymour, the 3 flow theorem by Thomason, are all proved for modular flows, because modular flows and integer flows are equivalent. So we just they claim that the integer flows, but it's always proved that for modular flows. The advantage of modular flow is when you just look at the flows. Usually we just look at the subgraphs. Then we just this subgraph has integer flow or has a flow here F1. So this subgraph has F2. If they can just cover the whole graph, we can add those two flows together. So once we add them together, you have for integer flows, you have to be careful. The total flow value should not be bigger than k minus 1. If it's bigger than k minus 1, then we would have trouble. But for zk, we know that we don't have upper bound. We only need to make sure that the sum of the flow values is not 0. So which is very nice. Okay, so this is the introduction to the flows of unsigned graph. So what is signed graph? So signed graph means for each edge we give it a sign, plus or positive or negative, 1 or negative 1. So in social network, so basically it's about plus means we know that two friends, just like it's the positive 1, and if two guys are enemies against each other, so it's negative 1. So we can just look at this. So but the unsigned graph, we just say that means every edge is positive. So edge is positive means that the signature is 1, negative means signature is negative 1. So unsigned graph means the signature of each edge is 1. So in the area of signed graph, we have an operation called switch operation. So what's the meaning of the switch operation? So this means at each vertex, you have a signed graph at each vertex. So some of edges incident with it are negative, some of them are positive. And so normally, in social network, in particular in the current situation in the United States, so it's polarized. So usually the Republican, if you switch from the Democrats to Republicans, so all the enemies become the friend, your friend becomes enemies. So that's not a joke. Actually, it's one of my best friends. She is the fan of Trump, and suddenly one day she always puts something on the WeChat. So one day I just try to respond it, and because I disagree with her, And one day she was mad at me. She just like disconnect me, so I cannot see here WeChat. So this is so polarized the situation here. So switching, actually in graphs, in the sign graph, we don't look at one graph. We just look at a family of, basically the best graph is the same, the signatures are different. So the two signatures are equivalent, means, for instance, if you get sigma 1 and sigma 2 are equivalent, it means you can always obtain the signature sigma 2 from 1 by switching at some vertices. So I will just give you something. So why we just look at the equivalent? So I will just give you some explanation a little bit later. So what's the from a social network? It's quite easy to explain the sign graph. So friends, positive and the positive edge, enemies, negative edges. But we're mathematicians. Okay? We're more interested in what's the meaning behind the mathematics. So actually, so you can just look at the embedding of the graphs on surfaces. So let's say G rho S be the embedding of G on surface S. So rho is the embedding, S is the surface. So you just draw the graph on the surface. And if you look at it locally, it's okay. It's can consider it as the planar graph. So at each vertex. If you look at the so you can just once you draw the graph on the sphere on the surface, the orders of the edges around this vertex is fixed, okay? Just like this. But you can also we know that if you look at, we have clockwise, counterclockwise, right? So if you look at this one, you can just pick this direction or pick this direction. It's up to you. So this is V here. So we have called pi V. Have a rotation here. You have two choices, is this way or that way. But locally, you can just say this is the clockwise or this is counterclockwise. Okay. So you just randomly just pick one. You have two choices. Pick a pi V. So we have each vertex. You have rotation. So we have a rotation system. And for the once you have a rotation system, you can define the signatures of the edges. So once you have a rotation system, locally you can always have like a band to include one edge. So just like you can look at this as on the piece of paper. So once you have the piece of paper, and if you see that, so those two edges, you can see that they have different rotations. So you can see this is a negative edge. And if they have same rotations is the positive edge. When we look at the piece of paper, so it's easy to tell which one is clockwise, which one is the counterclockwise. But when we have like the non-orientable surface, in particular when we have a Mobius span, a piece of paper will have two sides, right? You cannot, if you work on this side, you cannot go to the other side. But while the Mobius span is one side, so you can always walk from here, from this side to here. So if you just stand here, you can see that this side, this direction is clockwise. But if someone goes to the outside, the other one is clockwise, right? So that means you can just choose. That's why we can always choose two different rotations. Really depends on. So of course, when someone says that why I choose this one, because if you look at the outside, the Mobius span, then I would choose this one, and the surgeon might choose this rotation here. So does not change the graph. Basically, the graph is the same. The embedding is the same. So that's why. The only difference here is, you see that, so this is a negative edge. If I just change the rotation different, you can see this is a positive edge. So this gives us different rotation, gives us the different, and basically it's a switch operation to this vertex. Okay. So essentially those two graphs are the same, even the embedding are the same. So that means those two graphs should be the same. So that's why we only consider the equivalent signatures. So this tells us that any embedding will induce a signature assigned graph, depends on pi v. But no matter how you choose the pi v, so two different people, surgeon and I may choose different pi, but those two signatures are equivalent. Okay? So no matter which one you choose, you only have 2 to the n to the nth power choices. So no matter which you want to choose, our two signatures are equivalent. So this is the example. So this is the Pearson graph embedded on torus or projective plan. Now we know that projective plan can be represented by a disk. So you can see that. So this is x5. Look at the edge x5, x3. So first half go to here, go to boundary, then jump to the outside. So this is one edge. So the two parts of the edge x3, x5, x3, x3, x5. So this edge. So this edge is x1 go to B, then jump to B here, x4. So these are the two half edges of the whole edge x1, x4. So you can see that. So this one just got the embedding of the Pearson graph on the projected plan, and so those edges are negative edges. Okay? Or you can just look at rotation here. Or roughly speaking, you can another way to define the signature induced by embedding is if the edge passes through the cost cap all the times, it's negative edge. It passes through the cost cap even times, it's positive edge. So that's why if you look at the embedding on orientable surface, every edge you can just pick a pi v such that every edge is positive. So that's the embedding of the Pearson graph. And also, also you can see that this one, the first combination number of this embedding is 6, because the dual is K6. And another difference between the unsigned graph and signed graph is the orientation of the negative edge, since you have negative edges here. So the orientation here is, for positive edge, usually we just orient like V is initial point, the other one is terminal point. So initial, terminal. However, for the negative edges, we look at the two endpoints, you can see that both of the sides look like going out or going inside. In other words, we just cut this. The reason we want to look at half edges here, you can see that we have half edge here, half edge here. So cut the edge into two halves. So you can see that those two half edges have opposite orientation. But if you look at negative edges cut from middle, so two half edges have the same orientation. So for the negative edges, if two half edges are always oriented with the same orientation. Either both are out or both are in. So why we just orient the negative edges in such a way? Look at this example. So this is K4 embedded on the projected plan. Okay. So you can see this is one edge. So this is so those two edges basically is diagonal, and those. So for the projected plan, we know that so those two are the same faces. So those two are the same. So this is F. Okay. So here we only have 3 faces here. So if you just walk along this direction, you can see that on the positive edge, G is always on your right side, and H is. And once this is the only difference between the signed graph and unsigned graph. So once we know the orientations, the definition of flows and the modular flows are the same as the unsigned graph. So we have orientation. So we just sometimes we just call it bidirectional graph, because you can see that each edge will have 2 directions. We just orient each half edge. So we have the orientation of signed graph, then we just assign integer values, and we make sure that at each vertex, the total inflow equal to the outflow. For instance, for this one, so this is nowhere 3 flow. Look at this one vertex, we have 2 edges out. So the total outflow is 2 plus -1 is 1, inflow is 1. So the inflow equal to outflow. And you can also see that the maximum absolute value of the flow is 2, which is 3 minus 1. So that's nowhere 3 flow. So this one's modulo 3 flow. If you look at this V4, you can see all 3 edges are oriented in. So the total inflow is 3, which is 0 in this 3. So this is modulo 3 flow. And what's the motivation here? So for the flow theorem of signed graph is extension of Tutte's flow theorem of graphs on non-orientable surfaces. So we can prove that the G be a graph embedded on a non-orientable surface. And sigma S is the signed graph induced by embedding. Of course, you may see that the signature may be different, but all the signatures should be equivalent. So it doesn't matter which one. So if G is K-face colorable, then the signed graph admits nowhere 0 K flow. And just like the unsigned, the orientable surface for the sphere, first K-calculable is equivalent to K-flow. So for the projected plane, we still have this equivalence. So we can prove that if G is K-phase calculable on projected plane, if and only if it's the induced sine graph admits no zero K-flow. So for projected plane, they're equivalent. But in general, the K-phase calculable implies K-flow. That's one direction. So what's another difference? Okay, so still so far we don't see significant difference between sine graph and unsigned graph besides the orientation, right? So another significant difference, I think this is a significant difference between the sine graph and unsigned graph. So if you look at the matroid, so we know that the graphical matroid for the graphs is you just look at the incidence matrix. Incidence matrix is 0, 1 matrix for unsigned graph, and the minimal for unsigned graph. The minimal dependent set is what? Is a connected two regular graph, which is simple cycle. Okay. However, if you look at the incidence matrix of sine graph, because we have negative edge, we have positive edge, so this is a 0, 1, negative 1 matrix. If you look at incidence. So that gives us, if you look at the minimal dependent set, so we have 3 kinds of minimal dependent set. First, let's see with the balance, a circuit is balanced means it has even number of negative edges. Right. So if we have even number of negative edges, we can do some switch operation to make all the edges in the circuit positive. And unbalanced means that it has all the number of negative edges. So a signed circuit, so basically the minimal dependent set of a signed graph has 3 different elements. One is a balanced circuit. So basically, so this is like a circuit without all the edges are positive. And we have 2 others. This one is called short barbell. So short barbell is what? We have 2 unbalanced circuits. So each of them has all the number of negative edges. They will share at one vertex. So that's the one vertex here. So they're called short barbell. Long barbell is we have 2 unbalanced circuits and connected by a non-trivial path. Okay, so you can see that one vertex is a trivial path. But long barbell is connected by a non-trivial path. Okay. So you can see that for unsigned graph, the elementary element inside space is simply a circuit. However, for a signed graph, we have 3 different elements. And also, so which case, another annoying thing here is, so those 2 graphs, balanced circuit, short barbells, they admit nowhere 0, 2 flow. But this guy admits nowhere 0, 3 flow, no 2 flows. And for unsigned graph, a circuit always admits nowhere 0, 2 flow. So this just makes the flow of signed graph more complicated. A signed graph is unbalanced, so means it has unbalanced circuit. So of course we want to for unsigned graph, a graph admits nowhere 0 integer k flow for some integer k greater than equal to, as long as it has no bridge. However, for a signed graph, even you have complete graph, if the complete graph has only one negative edge, it does not admit nowhere 0 integer k flow, except k equal to 1. So it means because it does not have a signed circuit. If a complete graph has only one negative edge, you cannot have a signed circuit. So a signed circuit admits nowhere 0 k flow for some integer k greater than equal to if and only if every edge is contained in a signed circuit. So such graph is called flow-admissible. So no matter how, in general, we know that for unsigned graph, the edge connectivity plays significant role on the flow values. But for signed graph, there's something else. And also, flow-admissible signed graph may have bridges. So bridges are allowed for signed graph. So in the area of signed graph, the most important conjecture is due to Bouchet. Just as Shane told me that he just passed away. I think it's in the spring, March. Yeah. So he conjectured that every flow-admissible signed graph admits nowhere 0, 6 flow. And there are actually in his paper he only found one graph, which is the Peterson graph I just showed you, which does not have nowhere 0, 5 flow. That means the flow index of that graph is 6. So that's That's why he just used the 6th flow here. That's the only graph he had at that time. But right now we have a bunch of infinity many signed graphs which has nowhere 6 flow but nowhere 5 flow. So this is Pearson graph. So that's the found by Bouchet. So this one is the Q. So we can see that we have 3 negative edges, and it says that they just use computer search. I don't know how that is. So another way, another graph family of graph is if you look at for instance, look at C6. You just start with C6 with all positive edges, then you just add 1 negative here. So this is like for any circuit, positive circuit with length 4k plus 2, you can always do this. So it's easy to prove that those graphs, the flow index of those graphs are 6. They don't have nowhere 5 flow, but they have nowhere 6 flow. Actually, the proof is quite simple here. Also, it's quite easy to see that all those 3 edges must have the same parity. Either they're all odd or all even. So there are some known results, and actually the Bouchet in his paper he proves that every flow admissible sign graph admits nowhere 216 flow. And Zyka in his dissertation shows that 30 flow, and DeVos he just posted a paper around like 2012 on archive claims that he proved that 12 flow. And also that some kinds of special family graphs, for instance, series parallel graph, that can prove that it admits nowhere 6 flow, and also it's 2 negative edges. So 2 negative edges probably, if the graph has only 1 negative edge, it does not admit nowhere 0 integer k flow. It's not flow admissible. So that's why I can look at the 2 negative edges. So they can prove that if the graph has 2 negative edges, then Bouchet's conjecture is true. And for the high edge connectivity, you can see that 4 edge connected graph admits nowhere 4 flow, 8 edge connected graph admits nowhere 3 flow. And for the Keller graph, you can prove that it admits nowhere 4 flow. And also there's the paper just posted on the archive, and they prove that 5 edge connected graph admits nowhere 8 flow.
What was the regular Tutte's 4 flow conjecture? Was it 4 edge connected?
4 flow conjecture means the Peterson minor free.
Peterson minor free.
Peterson minor free, yeah. And 4 edge, that's the 3 flow conjecture. 4 edge connected graph admits nowhere 3 flow. Oh, by the way, so for the unsigned graph, it's quite easy to prove that 4 edge connected graph admits nowhere 4 flow. The difference here between signed graph and unsigned graph is, for the unsigned graph, we know span tree is connected, but for signed graph, the span tree may not be connected. And so we start to work on this the flows of signed graph since 2015. And so the result we want to prove here is we prove that every flow admissible signed graph admits nowhere 11 flow. So actually, as I mentioned, that DeVos, he just posted a paper which claims that he proved that every flow admissible signed graph admits nowhere 12 flow. And yeah, I'll just mention a bit later here. And then we'll also look at some special families of signed graph. For instance, if the graph does not have edge disjointed unbalanced circuit, which means does not have short barbell, does not have a long barbell, right? So then it's 6 flows. It has 6 flow. And if in case long barbell is troublemaker. Short barbell still has nowhere 2 flow. Balanced circuit still have nowhere 2 flow. So we can, if we exclude long barbell, and we can prove that it's still has 6 flow. Actually, in this paper, we try to see that what happens if we exclude the long barbell. We find out that almost all the flow theorem for unsigned graph can be transferred to signed graph without long barbells, but not all of them. For instance, Pearson graph still has Pearson graph has no long barbell, but its flow index is 6. It's not 5. And also look at the next the 2 negative edges, 3 negative edges. So we try to look at the 3 negative edges, so we can also show that it has nowhere 6 flow. Actually, the difficulty between 3 negative edges and 2 negative edges, so they're significant. Right now, we can have very easy proof for the signed graphs with 2 negative edges, but for the 3 negative edges, the proof is very ugly. I don't like that proof. Because we're mathematicians, we always like the beauty, right? So, and also another family of graph is called triangular kinetic graph. Triangular kinetic graph is, so for any two non-parallel edges, E1 and E2, you can always find a so-called triangle path. So you can always find a sequence of triangles. So a sequence of triangles, that means only two adjacent triangles share a common edge. So T1, T3 are disjoint. Yeah, so T1 because they don't have common edge disjoint. So as long as for any two non-parallel edges, you can find a triangle path to connect them. So this is called triangular kinetic graph. And for the triangular kinetic graph, it's quite easy to see that this graph admits nowhere zero for flow. So in 2008, in a paper by Fan, Lai, Xu, and Zhang and Zhou, actually they characterized the triangular kinetic graph, which does not admit nowhere zero free flow. So they just give a complete characterization. So when we look at this problem, so I had a visitor here, around just pandemic. So he came to visit me, and I tried asked him to look at the signed triangular kinetic graph. At first, I thought the problem is a 6 flow, and finally we managed to prove that every flow admissible triangular kinetic graph admits nowhere zero 4 flow, except only one. So this is only where the signed graph, the triangular kinetic graphs, whose flow index is 5, and the other triangular kinetic graphs, flow index is at most 4. So that's only the graph we have, instead of the infinite family of graphs. There's only one here. And we also constructed a infinite many triangular kinetic unbalanced sign graph that admits nowhere zero 4 flow, but no 3 flows. So that's kind of construction here. You have two even cycles, then you just put some edges there to make this 4 regular graph. And another thing is, also at that time, I gave since when we have lots of visitors there, we try to find some easy problem for them, for them to work on. So another family I was thinking is the 3-edge colorable cubic graph. So we know that for the 3-edge colorable cubic graph, it always has nowhere zero 4 flow for unsigned graph. So I just asked him to see whether we can prove this for verify Bouchet conjecture for this family of graphs. But unfortunately, at that time, we were able to prove 10 flow. We even were unable to prove 8 flow. And that's almost all the cases we had give us 8 flows, except one case. So we were stuck on one case, and then when just the editor and Martin they visited me 2 years ago, I just told them which part I was stuck. So finally, we were able to prove that every 3-edge colorable cubic graph admits nowhere zero 8 flow. And then we look at the extension. So we tried. Finally, we just extend this result to what? As long as the graph, the underlying unsigned graph admits nowhere zero 4 flow. If this unsigned graph admits nowhere zero 4 flow, then the corresponding flow admissible signed graph admits nowhere zero 8 flow. So a graph, an unsigned graph admits nowhere zero 4 flow. It includes lots of graphs: 3-edge colorable cubic graphs, Hamiltonian graphs, super-Eulerian graphs, and bridging planar graphs. So this guy make it bigger here.
So super-Eulerian is like partition into 2 Eulerian?
No, super-Eulerian means what? It means that it has a spanning. It has spanning Eulerian subgraph. From the point of view, super-Eulerian basically is the same as like a Hamiltonian cycle. So if we have a result on Hamiltonian cycle related to a Hamiltonian cycle, normally you can generalize this to super-Eulerian. It's just slightly bigger family than Hamiltonian cycle, Hamiltonian graphs. And another conjecture here is, as I mentioned earlier, that so far, those are the only graphs that's the basic graphs we know that does not admit nowhere zero 5 flow. So those are the graphs here. And we can just define 3 operations on the graphs. One operation here is 3 cut or 2 cut. So if you have a 3 cut, G2, G1, and G1 here, G2 here. So if you have a 2 cut or 3 cut, as long as G2 is positive or balanced. So if it's balanced, we can do switching operation to make all the edges positive. So once we make all the edges positive, we can contract G2. And we can prove that, so this graph admits nowhere 06 flow if and only if this graph admits nowhere 06 flow. So there's one operation here. The other operation is if you have degree 2 vertex here. Okay, so sigma, so this is E1, E2. And you can always replace this by one edge. And the signature of this new edge is the product of the signature of E1 and E2. So this operation here. And another operation is simply just add. So this is G1, you add, so this is G2, which is all positive. Right? So, and you can delete this one, get G. Okay, it's clear that, okay, so this 2, okay, so this graph admits nowhere 06 flow, if and only if this graph admits nowhere 06 flow. So those are the 3 operations. If you give me a sine graph, and I can apply those 3 operations to reduce the graph to one of those graphs here. So that graph always has nowhere 6 flow. The flow index is always 6. Okay. And the proof that, so this is called M here. So that just define the family of the graph. So it can reduce, apply those 3 operations to reduce to one of those 3 graphs. Pearson graph, the cube, so that's the 4K plus 2 graph, 4K plus 2 cycles. And the conjecture that, to prove that every graph in this family has flow index 6. The conjecture that those are all the graphs which has flow index 6. So that's the conjecture. Honestly speaking, I don't believe this conjecture is true, because we don't. There's the only things. Since these are the only graphs we know that has nowhere has flow index 6, and this one is computer search. It's obtained by computer search. So if you find another graph which has flow index 6, you can still apply this operation. So I'm not very confident that this conjecture is true. So I asked my students to see how to try to find counting examples. So we look at some very simple graph, just like K for minus free sine graph, and we can actually find out that the conjecture is true for K for minus free graph. So prove that every flow admissible K for minus free sine graph admits nowhere 05 flow, if and only if it's not reducible to one of these, because Pearson graph is not K for minus free, cube is not K for minus free. And we know that the class of kinetic K for minus free graphs includes a lot of other classes, just like series paragraphs. And as I mentioned earlier, that Kaiser and Lorova, they also prove that series paragraph sine graphs admits nowhere 06 flow. But they did not characterize which graphs has nowhere has flow index 6. So our result also characterized the flow, the K for minus free graphs with flow index 6, which is reducible to this graph. Okay, so these are the published results about the integer flows of sine graphs. And as I mentioned, that one of the most powerful tools in the field theory for unsigned graph is Tutte's result, which is integer K flow is equivalent to zk flow. However, this theorem does not work. It fails for sine graphs. But we still can use the modular flow or the zk flows to study integer flows. So this one you can see that, so we have 3 negative loops. So they're called negative loops. So this graph has so this is nowhere 0z3 flow. You can see that this vertex, all 3 edges in, so the total inflow is 6, which is 0 is 3, this 3. So those are the balance. So there's nowhere z3 flow. But this graph does not admit nowhere 0 3 flow. It does not admit nowhere 0 4 flow. it admits nowhere 0, 5 flow. So we have only 5. This graph only has nowhere, the flow index is 5. So the modular flow or the Z-cat flow is still a very important tool for us. So to prove our 11 flow theorem, we first extend Seymour's 6 flow theorem. Actually, as I mentioned, that he did not prove the integer 6 flow. He just proved that Z2 by Z3 flow to sine graphs. So we prove that every flow admissible sine graph admits a nowhere 0 balanced Z2 by Z3 flow. Balanced means the support. Okay? If you look at the edges in Z2 with non-zero edges in Z2, there are even number of negative edges. So they're called balanced Z2 by Z3 flow. So actually, this result is due to a divorce. Okay, it's not our result. And since the divorce posted this one together with his 11 flow theorem on archive, and when we use this theorem to prove our 11 flow theorem, so when we submit the paper to JCDB, William Moha suggests that we just combine the paper. So we had to rewrite it. His proof was quite long and it's not easy to read. So we just reorganized the proofs. There's some small gaps, but easy to fix. So I would say that this theorem is meant due to the divorce. And once we have Z2 flow, so we can convert, or we can just cover Z2 flow with integer 3 flow. We can cover. We just basically it's not covered, so we just convert this 3 flow into integer 5 flow. Then we just look at this. We just look at the 5 flow here. I think that's the F1 plus 3F2. Okay, so this give us normally it give us 15 flow. Okay. How to get 11 flow? Actually, in this lemma, we just have very nice lemma here. This is not just any arbitrary 5 flow. We have very, very nice 5 flow. This is 5 flow means 5 flow means what? The flow value is 1, 2, 3, 4. But for this 5, from here to get this 5 flow, no edge with flow value 3. No edge with flow value 3. So 3 does not appear. And we also know that if the flow value of edge is 4, then there must be a bridge. So this just gives us try to calculate that we cannot get this is indeed 11 flow. It's not 15 flow. So the converting converting modular flows to integer flows is still a very important tool for us. And actually, divorcing that paper on his 12 flow paper, so he also proves that if k is odd integer, and if it has nowhere 0 zk flow, then it has nowhere 0 2k flow. Means this 3 flow give him this integer 6 flow, this 5 flow give him 10 flow. This is only for odd integers. Although in his paper he just only mentioned that prime, odd primes, but his work just works well for all integers. You don't have to change anything. And the reason that Chen and Fan they just also find that improve that result to 2k minus 1 flow. From here you can see that one particular interesting case is if k is 5, so z5 flow implies what? 2 times 5 minus 1 is 9. So z5 flow implies 9 flow. And since we already have 11 flow theorem, so of course z6 flow implies the 11 flow. Z6 always implies 2k minus 1, and Z7 flow implies also 11 flow. So we don't need to look at the large case, or we need to look at the small case. So when k is 2, Z2 flow, how to convert the Z2 flow into integer flows? So actually, as I said, lots of people they didn't notice that. So I want to mention that. Because the divorce paper is not published, and most people just cite their paper. So actually, they prove that if the graph is flow-admissible and it admits nowhere 0 Z2 flow, then it admits nowhere 0 Z4 flow. And Chen and Fan they also found that the kind of improves the result that we know that the Z4 flow means what? We have flow value 3. They can also prove that there must be a circuit such that all the edges with flow value 3 or negative 3 are on this circuit. So they can just kind of like control of the edges with flow value 3 or negative 3. It might be useful, so I still don't know how. I feel that it might be, it's useful, but I don't know how to use this. Then we look at the k equal to 3, 4, 5. So when k equal to 3, we have admissible nowhere 0, 5 flow, so that's the way to prove the 11th flow theorem. And for k equal to 4, we can prove that it's admissible nowhere 0, 8 flow. So that's for even ones. Okay, so for the odd ones, they have 2k minus 1, but for even k's, we don't still have 2k. And when k is 5, and we know that when k is z5 flow implies what? Implies 9 flow. But if we just restrict that graph to be bridgeless, then it admits nowhere 0, 7 flow. So 5 and z5 plus bridgeless implies 7 flow. But without bridges, it implies 9 flow. So that's the. Yeah, it took us several years to figure out how to just convert Z4 flow into an integer 8 flow. So finally, just to give you some like we have one operation which is very useful. To prove this one, we just motivated by the proof of this theorem. So the idea to prove this one is to prove that if G admits nowhere 0, 4 flow, then the sine graph admits nowhere 0, 8 flow. Just like the lots of the graph theory problems, we first step is try to reduce the problem to cubic graph. So the first step is we prove that every flow-admissible sine graph whose underlying graph is cubic and 3-edge colorable admits nowhere 0, 8 flow. That's our first step. So because this one is quite the one we have cubic graph is quite easy. 3-edge colorable. You can look at the 3 color classes, the 3 mutual edge disjoint perfect matchings. Then you look at the parities of the number of negative edges. You can just manipulate, try to get 8 flows. And so how to reduce the problem to cubic? So there's one reduction here. So if the graph has nowhere 0, 4 flow, by Tutte's theorem, it has nowhere 0, 1. It has nowhere 0, Z2 by Z2 flow. And non-zero elements in Z2 by Z2 are 1, 0, 1, 0, 0, 1, 1, 1. So basically it's kind of like it's a 3 coloring, right? You can color graph with 3 colors. And for non-cubic graph, each color class is not a perfect matching, and it's called parity subgraph. Okay, so let's see. I'm going to use this. And one thing we can just show that. So those are the ABC. So ABC. So A is the number of edges with a flow value 1, 0. The number of edges with flow value 0, 1. The number of edges with 1, 1. So this we can prove that they have the same parity. Either all 3 of them are odd or all 3 of them are even, okay? Because it's a flow, so the sum should be 0. So once we have this one, we can try to just like reduce the problem to cubic graph. So those are the odd edges, let's say with 1, 0, odd edges with 0, 1, odd edges with 1, 1. So depends on the parity. If all of them are odd, or one of them all of them even, but one of them is 0, we can simply just blow this up into a cycle, into a circuit here. We blow them into a circuit, and we just all the blue edges are consecutive, all the yellow edges consecutive, all the red edges are consecutive. Then we can just put the color those edges. So that gives us a cubic graph. And so all the other cases, if all of them are even, but none of them is a 0, so we can just have to twist a little bit, because we have to manipulate the calculation. So we can see that we have consecutive the blue edges here except 1. So yellow edges are consecutive, red edges are consecutive, so the blue edges, but we just put one blue edge between yellow and red. So that's kind of the trick to reduce the problem to cubic graphs. And we just modify modify this trick to prove that Z4 flow implies integer 8 flow. So that's the that result just motivated by the idea of this one. Because this one actually, we were stuck. We were stuck on this problem for quite a long time. Because at least since for the other integers, we know that zk flow implies 2k flow by divorce the theorem, which is it's not that difficult to prove. So therefore it's natural to ask that how about the even integer k? Z2 flow implies 4 flow, and Z6 flow implies integer 11 flow. We already have 11 flow theorem. So the only remaining case is k equal to 4. So we were stuck with this for like probably for 4 years, 3 or 4 years. Then when we look at this the flow theorem motivated by the ideas, we just modify that idea to get through this case. So that's probably all I want to thank you very much.
Thank you. Any questions? So I have a question about, so you have this characterization when you have a no K4 minor, then you can characterize when the graphs have
Yeah.
a lower 0, 5 flow. Is there any work on like forbidding odd minors for this case? You forbid odd minor and then try to extend the existing.
It's very hard. It's very hard. Yeah.
Because we are talking about signed graphs, so it makes sense to.
Yeah,
about,
I see it.
odd
So
minors.
even for careful minor free graph, the proof is not that easy.
Uh-huh.
Yeah, for careful minor free graph, it's easy to prove. For unsigned graph, it's easy to prove that it means nowhere 0, 3 flow. But for signed graph, it's definitely I was thinking probably the next step is look at K5 minor free graphs. But the problem is we don't have many tools to apply. Just like for the triangular kinetic graph. For the triangular kinetic graph, since we cannot use the modular flows or zk flows. We always work on the integer flows. That's really just make the proof very, very long. Yeah, actually, so for me, that since I have been working on this for 10 years, and I think I just exhaust all the methods I can come up with. So that's why we just in order to make a big breakthrough, definitely we need some new ideas.
Any other questions?
That's what you asked.
Right, if there's no further questions, let's thank the speaker.
Thank you very much.